roll response of ships in waves is a complex phenomenon influenced by a large number of factors, including ship hull forms, appendages, steering, speed, direction, loading condition, and of course wave height and period. Roll is particularly dangerous to ships, for it can reach large values, jeopardizing the stability of the ship and endangering its crew and its cargo. Even when roll does not reach such extreme values, the effect of accelerations on cargo can result in severe damage. In this video, we will explore why large roll can occur in particular conditions and what can be done to limit it. During late October 1998, sustained Beaufort Force 11 to 12 wave conditions were encountered by a C-11 container ship in the North Pacific. Satellite wave measurements indicated that significant wave heights ranged from 12 to 14 metres during this period. In an effort to reduce roll motion, the master reduced speed and headed the ship into the seas, as would be normal practice in such events. Nevertheless, during this time the vessel took an especially severe roll, to an angle of about 35 to 40 degrees. A substantial number of deck-stowed containers were either damaged or lost overboard, and extensive damage was also suffered by the ship's equipment. What caused this severe roll, and why did established navigational procedures fail to reduce it? To help answer these questions, we will look at some basic theory of ship motion, to understand how roll is initiated, and what contributes to increase or reduce its magnitude. This will allow us to have a better understanding on how to use operational guidance tools to minimize the risk of large roll motion. First of all, though, it is of paramount importance to understand that large and at times violent roll motion are a very real danger, possible in most sea states, no matter how competent the crew or how new, large or good the ship. Captain Carney, the master of the post-Panamax container ship President Adams, recalls his encounter with HEC Parametric Roll as an unexpected and unnerving experience.
As the motion of the ship and the pitching started to increase, what we did was we reduced to 83 RPMs and then finally to 70, and then we went down to maneuvering full. And maneuvering full, the ship was riding the storm out very well, doing not pitching, but in a very, in a very regular motion. And we figured that, we were about 250 miles from Seattle, from the coast, and we figured that we would just ride out the storm, and then in about 18 hours it would pass, and we'd just proceed into port. At 4 o'clock in the morning, when the watch changed, I went with the second mate, and we made a tour of the vessel. We went through the tunnels and went up to the forepeak and looked around, and everything seemed to be fine. About an hour and 15 minutes later, after talking with the chief mate, who was on watch by then, I went below to my cabin, and I was there about 5 minutes, and the ship took went into a very violent series of rolls. And it was rolling so violently that it took me a while just to be able to negotiate one deck up, to get up the ladder and get up to the bridge and see what had gone on. When I got up to the bridge, the chief mate was visibly shaken, because it was what I believe affected him, as it did all of us through the night, was for a seaman, we are trained, and through experience we know what to do in a head seas, but to roll violently while in a head sea condition is really outside the norm, and it's not something that's to be expected or anticipated.
Roll is a dynamic oscillation of the ship around its longitudinal axis. As such, it has the same nature of any other periodic motion, like that of a swing. As in the case of a swing, gravity constantly tries to bring back the ship to its initial equilibrium position. This phenomenon is known as restoring, and in the case of the ship, it is stronger when the GM is large, whilst for a swing, it is stronger when the length of the swing is short. Just like a swing, the time to complete a cycle is the same no matter how large the oscillation. This time is known as the natural period, and in a ship it is inversely proportional to the ship's GM, while in a swing it is directly proportional to its length. In other words, the smaller the ship GM, or the longer the swing length, the longer the natural period. The first parameter influencing roll is GM. Just like a swing, the ship roll would naturally die out thanks to the damping caused by viscous losses, which are promoted by the presence of hull appendages such as bilge keels and passive anti-roll fins. In a swing, these losses are mainly due to friction at the bearing and the air viscosity. In order to sustain motion, an external excitation is needed. In the case of a ship, this is provided by the action of the waves. In both cases, the effect of the external excitation gets stronger as the amplitude of the exciting force becomes large and as its period approaches the natural period. In the case of a swing, this means pushing at the right time. In the case of a ship, the magnitude of roll becomes larger if the wave height increases and if the wave's encounter period is close to the ship's natural roll period. In these conditions, we say that the ship is experiencing resonant synchronous roll. When in resonance, the roll motion is only limited by the amount of damping available, and roll angles can reach very large values. Note that a large force is not necessarily sufficient to produce a large motion. Indeed, if the excitation is timed incorrectly, its effect might be negligible, when encounter period is very different from natural period, or even act as a damping element, when encounter period and natural period are close, but the exciting force is timed to counteract the roll acceleration. Anti-roll fins work on this principle. Three other important parameters influencing roll are therefore viscous damping, wave height, and encounter period. In order to see when synchronization between wave and roll motion is possible, we need to examine how the wave period encountered by the ship changes with ship speed and direction. In general, when a ship is traveling in quartering head seas, the encountered wave will have shorter periods and appear less regular. The higher the ship speed, the stronger the effect on wave periods. By converse, in quartering following seas, encountered wavelengths and periods will be longer and more regular. Again, the higher the ship speed, the longer the waves. For all intermediate points of sail, the effect of ship speed on wave encountered period will vary continuously between these two values. The largest roll excitation amplitudes will occur when the sea is close to the beam, whilst in straight head or following sea there is no direct roll excitation from the waves. Nevertheless, for a number of large ships, the beam sea condition is not resonant because the wave's modal period is sufficiently different from the ship's natural period for most loading conditions. For instance, when a ship's natural period approaches 30 to 35 seconds, the ship is more likely to suffer resonant roll in quartering seas than in beam seas. Our final two parameters influencing roll are therefore wave direction and ship speed. From the examination of the previous concepts, we can therefore observe that a good ship might be the one for which directly excited roll is minimal for most loading conditions. This means that the range of operational GM values is such that the ship's natural frequency is far from any wave frequency that the ship is likely to encounter in the range of normal service speeds for all points of sail in all sea states. For the worst condition, the amount of damping provided by the ship's anti-roll systems should be sufficient to limit the roll oscillation to small values. Although desirable, such ship design is not always possible to achieve in reality. Of course, since in general it is always possible to alter course and speed to avoid excessive roll, there is no real need to seek such an unrealistic design. It is much easier to exploit the effect of speed and course on the encountered wave period, to remove it from the ship's natural roll and avoid undesirable roll motion. For example, in the loading condition assumed, the ship in this animation has a natural roll period of 12 seconds, which is close to the wave period. For this reason, it experiences significant roll motion in beam C. By changing heading to following C and maintaining its speed of 15 knots, the ship roll reduces drastically. Also, by changing heading to head C and reducing its speed to 10 knots, the ship roll reduces significantly. To some extent, both these maneuvers have produced the desired result, and one might be more desirable than the other for a number of different operational reasons. Nevertheless, both might expose the ship to other mechanisms capable to excite very large roll. pure loss of stability, broaching to, and parametric roll. In order to make the right decision, we need to understand what these phenomena are and in which conditions they can occur. The phenomenon of pure loss of stability is a well-known instability that can occur in following sea. Pure loss of stability happens when the ship rides the crest of a wave of approximately the same length as herself. In this condition, the ship's GM can reduce significantly, and the ship becomes sensitive to any disturbance, such as cross seas or manoeuvring forces. As the probability of such disturbance increases with the time the ship spends on the crests, pure loss of stability is only likely in following sea, when the ship speed is such that the ship encounters only nearly regular waves. This happens when the ratio of ship speed in knots and observed wave period in seconds is between 0.8 and 2. The conditions for pure loss of stability are: the ship is at speed in following sea and the encountered wavelength is close to the ship length. The ship speed approaches the wave group velocity. The wave height is sufficient to reduce the ship's stability significantly. In these conditions, direct excitation from cross seas can produce large roll motion. Note that for large ships, these conditions can be met in both shallow and deep water. For example, the period of a wave of the same length of a 250-metre ship in deep water is 12.6 seconds. This means that the ship can be in danger of pure loss of stability for all speeds between 10 and 25 knots. Similar conditions to those that promote pure loss of stability also initiate broaching to. Broaching to is the term used to refer to a loss of steering control caused by surf riding and leading to a rapid change of course of the ship from following sea to beam sea. This violent change of course almost inevitably causes large roll motion and rapid capsize as a result of the concurrent action of wave excitation, centrifugal force in the turn, and increased lift on the hull. The conditions that lead to broaching are almost the same as those leading to pure loss of stability, namely, the ship is at speed in following sea and the encountered wavelength is close to the ship length. The ship speed approaches the speed of the wave. The wave height is sufficient to induce surf riding. In these conditions, particular stern forms, hull proportions, and insufficient rudder areas all increase the probability of broaching to. Note, though, that unlike pure loss of stability, these conditions can only be met for large, slow ships when sailing in shallow water, where waves of the appropriate length start feeling the bottom and slow down. For example, a ship of 250 metres length needs to be travelling at approximately 23 knots in water 15 metres deep to match the speed of a wave of the same length. In deep water, the same ship would have to run at 38 knots. To reduce the risk of pure loss of stability and broaching to, the International Maritime Organization has issued some specific guidelines, known as the MSC Circular 1228, revised guidance to the master for avoiding dangerous situations in adverse weather and sea conditions. The masters should be familiar with these guidelines and be able to use them. Nevertheless, it is important to remember that their applicability might vary from ship to ship, and that they cannot be a substitute for a proper understanding of the nature of ship motion. The types of roll we discussed so far have been known for a long time, and operational guidelines to avoid them are well established. The case of parametric roll is different. This phenomenon that was once regarded as just another following sea instability has instead been observed in both head and following sea in a number of occasions on many different ships. These include a number of fishing and cruise vessels, as well as the container ship APL China in 1998, the President Adams in 1994 and 2003, and the car carrier Wallenius Aida in 2003 and 2004. This phenomenon is therefore not limited to any one type of vessel, and can also occur in moderate seas. The Aida reported roll angles in head sea in excess of 15 degrees in just 5-metre significant wave height in February 2004. The master of the President Adams describes his experience of HEC Parametric Roll as follows.
That night, while in this storm, we experienced a series of 5 extreme rolls. And by an extreme roll, I mean over 35 degrees. The electronics officer was in the chart room during one set of rolls, and he witnessed the clinometer peg out at 45 degrees. Anybody who goes to sea knows that a 45-degree roll on a 903-foot ship is extreme. Another thing that we experienced during this rolling period was the speed of the rolls. They seem to us to be very fast. Outside, again, another phenomenon that seemed to us to be outside the normal experience of a mariner, which caused the ship to roll violently to port, to starboard, and back again. It didn't take long for us to realize that there was a pattern, and it was something that we finally were able to anticipate, and that was the signal for us to just hold on as the ship would enter another series of these parametric rolls. What would happen is that the ship would be in a natural pitch motion. It would get into this motion of pitching, and then there would be a shudder as the bow fell into a very deep trough. And once it would fall in, almost like falling into a hole in the sea. And once we felt the bow shudder like that, and this shudder would naturally extend throughout the ship, we knew that another set of these rolls were coming. And then we would hold on, and then the ship at times would pitch one more time, and sometimes would immediately go into a roll. The first roll generally was a moderate roll, but by the second or third roll, she was rolling violently, almost a sensation of flopping or flipping from side to side. Another experience that in discussing this with the officers and crew who were there for this, there was a sense of acceleration through the water as the ship rolled heavily to one side. It almost felt as if she was surfing the waves on the side of the hull. One of the things that I did come away from this experience was that now when we're in head seas, very big head seas, we time the pitch period, because it is a fact that if the pitch period is half of the natural rolling period, you are susceptible to this type of parametric rolling. And it's something that we never really timed or paid that much attention to before, but it's something that's of primary concern. Our experience with the parametric rolling also was that probably the most efficient way of getting out of it would be a course change, a radical and aggressive course change, and by this I mean at least 90 degrees to break the lock that you're in with the seas. Accompanying course change, I also recommend a change in speed. On 4 occasions, I took the con and I changed course and speed. Twice I decreased speed. I went to half a head, and on 2 occasions I increased speed to 65 turns. I believe that a change of speed also helps you or improves your ability to get out of the parametric rolling that you're in. But the most important thing is to take aggressive action and make large course changes, 90 to 100 degrees.
The term parametric roll has been used to describe large roll motion, which is not excited directly by the wave. This means that a ship simply pitching in head or following seas can start rolling heavily in a totally unexpected manner. In general, the following conditions need to be satisfied for parametric roll to occur. The ship has significant bow flare and stern overhangs, and the encountered wave is moderately high, with a wave length close to the ship length. The encountered wave period is close to half the ship's natural roll period. If the damping provided by the ship's appendages is low, parametric roll can occur whenever a small disturbance initiates it. Video footage recorded during model tests at Marin Seakeeping Basin will help us understand the nature of this phenomenon. The sequence of events characterizing a parametric roll episode is as follows. The ship is riding the waves, pitching but not rolling to any significant extent. As a result of a small disturbance, such as rudder or cross-seas action, roll motion is initiated. The rolls start small but quickly grow to large amplitudes. A series of large amplitude oscillations is then experienced, with the ship pitched down by bow each time the roll on either side reaches its maximum. These large rolls last until a new disturbance, rightly timed, disrupts the synchronization between roll and pitch motion. The ship then returns to pitching without any significant roll. Two phenomena occur that contribute to fueling this large unexpected roll motion. The first effect is the oscillation of the ship's GM. When a ship is in a wave crest, her roll restoring moment is reduced significantly. This is because the water plane area cut out by the wave is smaller than the one in calm water. When it is in a wave trough, the water plane area instead increases significantly as a result of bow flares and stern overhangs immersion. For this reason, her roll restoring also increases. As the waves succeed each other in a following or head sea, the ship's GM oscillates between its maximum and minimum values with the same period as the wave. This oscillation of the roll restoring moment can produce large roll amplitudes if its timing is right. To understand why this is the case, let's go back to the parallel between ship roll and swing oscillations. As we noted earlier, to make the swing high, what is really important is that each push is timed correctly. When no one is pushing, it is still possible to swing higher and higher by kicking one's feet and leaning back and forth with the right timing. This motion of the swinger's legs is effectively changing the swing's restoring moment in the same way as the wave changes the ship's GM. Much in the same way as it is important that feet go up when the swing is going up and back when the swing is coming back, to have parametric rolling, the ship has to be rolled to one side when in the trough of a wave and to the opposite side when in the next trough. Note that for this effect to be correctly timed, we need to have half-roll cycle, from the max roll to one side to max roll on the other side, every 2 wave troughs, a complete wavelength. Therefore, we need an encountered wave period close to half the ship's natural roll period. The other effect contributing to parametric roll is the coupling with pitch motion. Simply put, coupling of pitch into roll can be seen just as an additional increase of the roll restoring moment in the wave trough, due to the further increase in water plane area created by the pitch motion. If the ship has significant bow flare and it is pitched bow down in the wave trough, the water plane area cut by the wave will be larger than that at zero pitch. As a result, the roll restoring moment is further increased. Note that pitch coupling is not strictly necessary to have parametric roll, but it makes it much more probable and significant. Now that we have an appreciation for all the elements influencing parametric roll, how do we recognize a potentially dangerous situation, and how do we avoid letting it develop into a catastrophic event? As we have seen, one of the conditions necessary for parametric roll to occur is that the encountered wave period is close to half natural roll period. Therefore, to check if the ship is in danger of parametric roll in head or following sea, we need to estimate or time the ship's roll period and measure the ship's pitch period. If the roll period is close to twice the pitch period, then the ship might experience parametric roll. If the ship is in this condition in moderate to large seas, it is generally advisable to change speed and course. If a permanent change of course and speed is not possible, there is still something that the master can do to minimize parametric roll. As we have seen, large roll oscillations depend on good timing between pitch and roll. Disrupting this timing by maneuvering aggressively during a parametric roll event can contribute to breaking the lock and reducing the number and size of the large rolls. Of course, depending on ship loading condition and sea state characteristics, the same change of speed and heading might work in one occasion, but lead to an even more dangerous situation in others. Luckily, there exists a number of operational tools that are designed to make the task of choosing the right course of action easier. For instance, polar plots like the one shown here report for each sea state and GM the ship's speed and headings that might or might not be desirable. Choosing a speed and heading in the light-coloured areas, the ship's master can avoid dangerous roll amplitudes whilst optimizing course. Polar plots to avoid synchronous resonant roll have been available for many years, but it is only recently that the technology has been developed to include also parametric roll and the other instabilities we explored in this video. Furthermore, a simple computer program can allow a swift retrieval of the right plot with minimal data entry, when the polar plot software is directly linked to the ship's loading software. Finally, it is important to remember that all active and passive systems designed to damp roll, such as bilge keels, fins, and anti-roll tanks, are also generally effective in reducing the risk of parametric roll. Most of these systems become less effective as the ship's speed decreases, with the exception of anti-roll tanks. When properly tuned, anti-roll tanks would improve the resistance of a ship to parametric roll substantially. Of course, all active systems need to be operational and functioning for their benefit to be realized. In this sense, proper maintenance and a good understanding of their functioning is of vital importance. Whatever the method, it is always a good idea to keep roll motion under control. In normal operational conditions, large roll amplitudes might not immediately endanger the ship, but they will already have a considerable effect on lashed cargo. In the case of container ships, the forces acting on containers are due to the combined effect of gravity and ship accelerations. As the ship rolls to one side, the transverse component of gravity acting on the deck-stowed containers increases dramatically, so that when roll reaches 30 degrees, this force equals 1/2 the weight of the container. If a ship is rolling and pitching synchronously, as happens in parametric roll, the pitch acceleration will add on to this gravity component, increasing the total transverse force and the internal loads it produces. This animation illustrates changes in lashings tension, racking, corner post tension, and corner post compression, which occur as the ship rolls. All these internal loads generally reach their highest value at the maximum roll angle. Therefore, the prediction of the maximum roll angle that a vessel is expected to experience during its lifetime is an important aspect of designing a container securing system. Should the roll angle exceed the design assumptions, the risk of damaging or losing containers increases. Should the containers be lashed incorrectly for their size, or asymmetrically, failure would almost be certain. For reasons similar to these, it is always desirable to keep roll motion as low as possible, no matter the type of ship, be it a container ship, a ro-ro, or a bulk carrier.